Hello everyone, welcome to another hands-on session. In this hands-on session, we're going to discretize a mesh which has a circular void in the middle of it. As you can see here, we have a slightly different mesh compared to the previous one, where we had a uniform mesh, and the parameters were P and M for the dimensions of the uniform mesh. But this time, we have the parameters P, M, D1 and D2 as well. And then finally, we have a new parameter, which is the radius of the circular void in the middle of the mesh. One other difference is that the parameter M is not here, but instead it defines the pieces inside these four regions. So this is what we're going to do today. And we're also going to look at the final form of the code here. So this is what we're aiming for in this session. As you can see, we have the void inside. So there's no elements inside. Also, the numbering is a little different compared to the uniform mesh, where the nodes go from 1, 2, 3, 4, 5, and instead of going here, it just prefers a circular path. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then it switches to the inside of the mesh. So 17, 18, 19, so on and so forth until it comes to the end, which is 64 in this case. So this is the mesh where the parameters are R is 0.2, the radius is 0.2, D1 and D2 are 1 still, P is 4, and then M is 3. So we have 4 pieces here, and then we have 3 pieces on the inside. So this is the mesh. Now, in the generate function, what changes is that we're going to write another function in another Py file. So I created this file instead. So instead of importing uniform mesh, we're going to import void mesh from this file. And then also we have defined the parameter R here, 0.2. And then finally, we're going to call void mesh instead of uniform mesh in this line. And the rest is pretty much the same for the generate.py file. So that's it. Now, let's start by defining the function in here. So def void mesh, and it's going to take these parameters here. And then before that, I also would like to import 2 libraries that we're going to use inside this function, which are numpy as np. And then I'm also going to need math to use the pi number. So that's all the libraries that we're going to use. Now, just like before in the uniform mesh, I'm going to define the corner coordinates of the whole mesh. So it's going to be 4 coordinates. And then these coordinates are going to be the same as the uniform mesh. So we're going to have D1 to 0, 0 to D2, and then D1 to D2. So basically, I'm defining the corners of the mesh, just like before. So I'm not going to explain it all over again. The problem dimension is, again, 2 in this case, just like the uniform mesh. So this time, the number of nodes is going to change slightly. Now, we have to divide this mesh into 4 regions. So 1, 2, 3, and 4. As you can see, we have 4 regions. And then in each region, we have M pieces right here and then P pieces right here. So if I were to calculate the number of nodes for a single region, so let's say region 1, it would be M plus 1 times P plus 1. Because if we have M pieces here, it should be M plus 1 nodes. And then if we have P pieces here, then we should have P plus 1 nodes here. So M plus 1 times P plus 1 is going to give me the number of nodes in region 1. It'll be the same for region 2, M plus 1 times P plus 1. But there's something that we should not forget about. These diagonal lines are shared between these regions. So we should subtract them when we're calculating the number of nodes for region 3 and 4. So what we're going to do here is 2 times P plus 1 times M plus 1, as we said before, because we have region 1 and 2. And then we also have a number of nodes for 3 and 4. But this time, since we already covered these 2 lines, for example, it should be P minus 1 times M plus 1. So we actually subtract 2 from P because we covered these 2 lines. And M is going to stay the same because it represents the pieces on these diagonal lines, but not these lines on the outside. So the same can be said for region 4. And then if we multiply it by 2, this will give me the total number of nodes in the whole mesh. So that's done. Now, the number of elements is simply going to be, so let's say for region 1, we have M pieces here and then P pieces here. So M times P will give me the number of elements in region 1, just like in the uniform mesh. The same can be said for every region, and since the elements are not shared between the regions, we can just directly say 4 times P times M. And then finally, we have nodes per element, which is 4 for D2QU4N, if you remember. So this completes the basic information regarding the mesh. Now, let's move on to the node part. Let's create an NumPy array full of zeros for the node list. So np.zeros, just like before, it will be number of nodes times problem dimension. And then, just like before, we have to define the increments. So it's going to be exactly the same as before, but since both sides are divided by p, we're going to change the increment b that we defined for uniform mesh here with p instead of m. Other than that, it's going to be the same. So let's go ahead to the uniform mesh code and then copy these 2 lines and then paste them here instead of writing them all over again. And then all we have to do here is change this m to p. Now, we can move on to region 1. So this is going to be the calculations for region 1. Every region will have their own node lists, and then we're going to combine these node lists at the end to represent the whole mesh. So I'm going to call the node list of region 1 core 11. Similarly, it's going to be core 22, core 33, and core 44 for the other regions. So let's create an empty NumPy array. And then the size of this will be the number of nodes times problem dimension. And then, as we discussed before, the number of nodes for region 1 is going to be m plus 1 times p plus 1. So let's do that. P plus 1 times m plus 1. And then it's going to be the problem dimension. So we're going to start calculating the nodes at the very bottom, which are these ones. So we're actually, in this case, we're calculating the nodes 1, 2, 3, 4, and 5. So we're only looking at this line. And then we're also going to write a for loop for the nodes on the void line, which are 49, 50, 51, 52, 53, although the numbering will be different initially, and then we're going to reorder the nodes. But just for the representation, we're going to calculate these nodes in that for loop. And then finally, we will need another for loop for the nodes in between. So it's going to be 17, 18, 19, 20, 21, and then this line, the nodes on this line as well. So we're going to have 3 for loops. Let's write the first for loop for I in range from 1 to p plus 2. So since the bottom is divided to p pieces, we're going to have p plus 1 nodes in this section. So that's why the loop goes from 1 to p plus 2. So the first value is going to be 1, and the last value is going to be p plus 1, since Python doesn't include the last member of the for loop. To calculate the nodes on this line, let's first calculate the x-coordinates of these nodes. So I minus 1, 0 for the x column is equal to, so initially when I is 1, this is going to be 0, so it's going to be the first node at the 0th index. This is going to be equal to q0, 0 plus I minus 1 times a, the exact same logic that we used in uniform mesh, as you might remember. And then we're going to do the same for the y values. So it's going to be I minus 1. This time it's going to be the second column. And then the values we have here is 0, 1. So essentially, looking at the distance here and then adding the increment and then calculating the coordinates of the nodes on that line, just like in the uniform mesh. Now, let's move on to the nodes on the void line here. So for I in range from 1 to p plus 2, again, the same logic here. This time, let's copy this. And then delete this as well. Now, this time, I have to start indexing the nodes from this point. So to come to this point, we have to calculate the number of nodes until we come to this point. So we have p plus 1 nodes here, p plus 1 nodes here, p plus 1 nodes here, and then when I come here, if I add 1, I come to this point. So it's going to be m times, so we have m pieces here, so m times p plus 1 brings me here. So let's do that. M times p plus 1 brings me here. And then I'm going to add the value I here. So let me just indent some lines so that you can see it more clearly. m times p plus 1 brings me here, and then if I start adding I, it brings me here, and then as I increases, I move along the other nodes as well. And then finally, since we're in Python, I have to subtract 1 because the index starts from 0. So that's the logic. The same logic applies for the y values as well. So let's just copy and paste it here. Now, as you can see here, the path is circular. So instead of using the distance, we have to use the angle as shown here. So what we're going to do here is multiply the radius by the amount of degrees that we traveled until we come here. And then as the for loop continues to increase the I value, we will move this arrow along this portion of the circle. So that's what we're going to do. So if we start theta as 0 from here, so this is going to be pi over 4. This is going to be 3 pi over 4. And then when I come here, it's going to be 5 pi over 4. And then I'm going to keep adding pi over 4 until I come here. So r times np dot cosine. For x values, we're going to use cosine. And then for y values, we are going to use sine, as you know from calculus. So I'm going to do 5 times math.pi divided by 4. So I come to this line here, this angle here. And then I'm going to keep adding the increment, which is pi over 4 divided by p, because this angle right here is pi over 4, and then we have p pieces. So if I divide pi over 4 by p, it's going to give me the increment angle-wise. So this is going to be I minus 1 times, so initially I don't want to add any increment because I want this point. So it's going to be I minus 1 instead of I. So I minus 1 times math.pi divided by 2. So let's just put this in another bracket, okay? And then we're going to divide this by p. I think I said 4 previously, but let me just correct it. This is 90 degrees, so it's going to be pi over 2. And then we have to divide pi over 2 to p to get the increment along this angle. So that's what we're doing here. Not pi over 4, but pi over 2. Let's make sure the brackets are correct. So this does this. Yes, yes, okay. So that's correct. And then finally, if you leave it like this, it will start calculating the coordinates from the 0, 0 coordinate from the origin. But we have to bring the center of the circle to this point. And as you remember from the uniform mesh, and then for this mesh as well, the dimensions were d1 and d2. So the coordinates of this point will be d1 divided by 2 to d2 divided by 2. So I have to move the x coordinates by d1 over 2 to bring the center of the circle to this point. The same can be said for the y values, but this time it's going to be sine. And then this has to be d2 because the dimension along the y-axis for the mesh is d2. And that completes the calculation of the nodes along void line. Now, all we have to do is calculate the node numbers on the lines in between these two lines. So I'm going to write another for loop here for I in range from 1 to m, and then for j in range from 1 to p plus 2. So the reason why this is m is because we already covered the lines at the bottom and the top. So we already covered the lines here and here. So we have to subtract 2 from m. So originally this had to be m plus 2, but if you subtract 2 lines, it has to be m. So the values for I will be 1 and 2 instead of 1, 2, 3, and 4. So that's it. For the other for loop here, with the j in here, it's still going to be p plus 2 because these two lines are still covered. So we want all these lines here. But this is not going to be the case for region 3 and 4 because these lines will already be covered in region 1 and 2. So stay tuned for that. Now, let's calculate the increment between these two lines. So essentially, I'm going to find the difference, the length between these nodes and these nodes, and then divide them by m to get the increment. So this is going to be the increment. So the distance between, let's say, 1 and 17, 17 and 33, and 33 and 49 is going to be my increment. So coordinate 11, the same as before, we discussed above, and then plus j, and then for index it's going to be minus 1. We will subtract, let's say, coordinate 11, j minus 1, 0, and then divide it by m. So essentially, what I'm doing here is finding the distance between the first line and the second line, and then dividing it by m, as we said before. It'll be the same for the y values, but this time we will have to change these to 1. The second column represents the y values, as you know. And now that we have the increments, we can now calculate the numbers for these nodes. So it's going to be coordinate 11 I times p plus 1 plus j minus 1, just like here. 0 is equal to, let's just copy this, and then plus dx, and then change this to I minus 1. So essentially what's happening here is I'm taking the coordinate of this node, let's say, I'm adding the x increment here, so I come here, which represents the x coordinate of this node. And then this is why we have I minus 1 here and then I here. This is going to be the previous node, this is going to be the current node. I'm adding dx to the previous node to get the next node on the next line. Again, it's going to be very similar for y values as well. So it's going to be 1, 1, and dy. So that completes region 1. Now, let's move on to region 2. Again, the size of the matrix will be the same, only the name is going to change. Then we're going to have the same for loop here. So I'm going to copy this. By the way, region 2 is the region at the top, if you don't remember. So we're looking at this region instead of this one. This was region 1 and this is region 2. So the only thing that we have to change in this for loop is the coordinates of the corners. So instead of 0, 0, and 0, 1, we have to put 2, 0, and then 2, 1, because that's the coordinates of these two corners. Now, the second for loop is also very similar. So let me just copy it from region 1. This time, we're going to come to 3 pi over 4, which is here. So imagine this line, this angle here. So it's going to be 3 pi over 4. And then I will subtract the angle as the for loop goes on. So from 3 pi over 4, so I'm going to travel from 3 pi over 4 to pi over 4. So to do this, we have to change this to 3 pi over 4 and then subtract this portion here to move to this direction. And then the rest is going to be the same. So this completes this part as well. And then finally, I'm also going to copy this for loop here. And then we also need to change the names of these NumPy arrays. So let me just do that. So 22, 22. This will be 22, 22. And yeah, that's it. This part can stay exactly the same as region 1. And this part's also going to stay the same for the other regions as well, but the size of the for loops will change, and we'll come to that. But this completes region 2. Now we can move on to region 3. And just like before, the size of the matrix will be this one, but this time, since we covered these two lines in region 1 and 2, instead of p plus 1, it has to be p minus 1, because we don't want these two lines since we already covered those lines. So I'm just going to turn this into p minus 1, and that's the only difference. Now, we can just copy this for loop from here. And then just like before, we're going to change the corner value. So it's going to be 0, 0 to 0, 1. And then since this time this is vertical instead of horizontal, instead of adding a to this value, we have to add I times b to this value. And then since we account for these two lines, it's going to be I instead of I minus 1. So that's the only difference. And since, as I said before, instead of p plus 1, we said p minus 1, the same logic applies here. So instead of p plus 2, it's going to be p, because we already covered these two lines. Now, we can also copy this for loop from the previous part and then we can modify it. The same logic applies here. It's going to be p instead of p plus 2. And then we also need to change the name of the matrices. So let me just do that. All right. Now, what we're going to change here is, first, I'm going to modify these I-1s into i's. The reason for this is because we want to avoid counting nodes on these diagonal lines, since we already done that. The same logic here. So that's why this is I instead of I-1. And then I'm also going to come to 5 pi over 4. And then that's going to be the only difference. And then finally, we have to change these to p minus 1s as well, the same logic. So we come to 5 pi over 4, which is this angle. And then I subtract the increment as the for loop goes on. So I'm moving towards this side. So from here to here. So I'm starting from 5 pi over 4, and I'll end up at 3 pi over 4. So that's what's happening in this cosine function. And the rest is the same. This completes this part as well. And then finally, we can just copy this part. The only thing that we're going to change here is this for loop. So instead of p plus 2, it's going to be p. As we said before, we've already covered for these two lines. So that's going to be p. And then that completes region 3 as well. Finally, we have the fourth region here. So let's just say region 4. And then let's not forget about changing the names of these NumPy arrays. All right. So now that region 3 is also complete, we can finally look at the final region, region 4, which is this one. So the size of the matrix will be the same as the third region, since we already covered these two lines here in region 1 and 2. So this is going to be the same. Now, I can also copy this for loop and then change the corner coordinates, which are going to be 1 to 0 and 1 to 1. So next up, we can copy this for loop from region 3. This time, we're only going to change where we're starting. So it's going to be 7 pi over 4. And then instead of subtracting, we're going to add the angle. So essentially, if we go 7 pi over 4, it's going to be this line, this angle. And then as the for loop goes on and the I value increases, I'm going to go towards this side. So I'm going from 7 pi over 4 to pi over 4. And this is what's happening here. Next, we can also copy this part. The size of the for loops are going to be the same as region 3, so nothing's going to change in that part. The only thing that I have to change now is the size, the names of these NumPy arrays. So let me just do that. I'm sorry, I keep forgetting these, but since we just do a lot of copy and paste, I kind of flow with the code. Let's just change these and move on. All right. I think we have missed something in these two matrices. So We also have to modify these plus ones for the same reason we modify these for loops. So don't forget to change these to p minus ones. I'm sorry, I forgot about that. So we're going to do the same for region 4 as well. And then that should be it. Now that we've created the node lists for each region, we have the node numbers for each region, but to simplify element generation process, we have to reorder these nodes such that it looks like this. So as I have said before, it should be 1, 2, 3, 4, 5. Instead of this being 6, this has to be the 6th node, and then this one, this one, this one, so on and so forth. So it's going to draw circles until it comes to the very end, at the very inside. So let's do that. You don't have to know the algorithm behind reordering the nodes, since there are multiple ways of doing this. I'm just showing one way to do this. So it's going to be the nodes. All right, as you can see, this is the algorithm that I use to reorder the nodes. If you really like to know what happens in here, in short, you have to place p minus 1 instead of p plus 1 for coordinates 44 and 33. And then we flip these numpy arrays to match the size. And then at the end of this, for loop, the nodes are ordered in such a way that they go like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth. So in a circular path. So that completes the reordering of the nodes. Now let's move on to the elements. So there are multiple strategies for element and node generation. For some strategies, element generation is kind of a hustle. By ordering the nodes like this, we significantly decrease the complexity of element generation. In short, we reorder the nodes above to simplify element generation, and you'll see why. So essentially, we're going to use 3 for loops in here, or let's say 2 for loops and 3 if blocks here to assign the element numbers into the element list, and that'll be it. In other strategies for discretization of void mesh, circular void mesh, it may take longer to assign the element numbers. So just like before, we're going to start with np.zeros. The size of it will be number of elements times node per elements, as you know. And then I'm going to assign a for loop here, which is going to be for I in range from 1 to n plus 1. And then for j in range from 1 to 4 times p plus 1. So if you remember the for loop for uniform mesh, it was from 1 to p plus 1, but this time it's going to be 4p from 1 to 4p plus 1. The reason for this is very simple. We're splitting our domain in 4 parts, and we're numbering nodes differently, going from outside to the inside. So essentially, we have 4 regions, and that's why we have 4p. So this part has p pieces, this part has p pieces, and p pieces. If you sum them up, it's going to give you 4p. which is why this is 4p plus 1. So the first value is going to be 1, and the final value is going to be 4p. So the first condition is going to be when j is equal to 1, just like in the uniform mesh. So let's start with I minus 1 times, this time it's going to be 4p, unlike p in the uniform mesh. I'm not going to explain this in detail since we already discussed this in the uniform mesh part. Minus 1 for index and 0 for the first number, for the first node number. And then this is going to be equal to I minus 1 times 4 times p plus 1. So as you can see, they're pretty much the same. But this time, this is going to be 4p instead of p. And then since it is the first, you can put j in here if you want, but it doesn't matter because j is always 1. So let's put j for simplicity. And then for the second node number in the element list, so let's say 1, the same logic applies here. I'm going to take this known node number in the element list, and I'm going to add 1 to it. Why? Because let's say I'm looking at this element. If I want to find this node number, I will simply add 1 to the previous one. So it's going to be 1 plus 1, which is 2, 17 plus 1, 18, and 33 plus 1, which is 34. So that's it. For the fourth node number, which is going to be 17 in this case for element 1, this is going to be equal to the first node plus 4 times p. So let's say p was 4 in this example. So we have 4 pieces here, 4, 4, 4, which is 16. And then if you add 16 to 1, it's going to give you 17. So whatever p is, if you add 4p to the first node number, it's going to give you this value. And if you add 4p to this, it's going to give you 33, and so on and so forth. So that's what's happening here. And then finally, for the third node, or let's say this is going to be 3 and this is going to be 2, the indexing. So for the third node number in the element list, I'm simply going to add 1 to this value. Because if you add 1 to 17, it's going to be 18, 34, and 50. It's the same logic as in uniform mesh. So the other possibility is that the elements at the very end of the for loop, so it's going to be 4p. So j is going to be 4p in the last loop for the second loop. So when j is 4p, we're essentially looking at the elements 16, 32, and 48. The problem with these elements is that the first node number is 16. The second one is 1, 17, and 32. So you can still determine these two numbers from the previous element, but these two numbers cannot be determined from the previous element because they are connected to the first element. So we have to define a different condition for these two node numbers. So here, the indexing is going to be the same for the element list, but this time I'm going to multiply it by I and then 4 times p. So essentially you add 4p until you come here and then assign 16 to this element. So it's the same logic as before. For the second node number, which is 1, it's going to be equal to I minus 1 times 4 times p plus 1. So essentially why we said I minus 1 here is because it's going to go to the previous set of elements. If we're looking at, let's say, 16, it's going to go to element number 1 and then look at this node. If we're looking at 32, it's going to go to 17 and then look at this node, and so on and so forth. So that's why we have I minus 1 here. And then 4 times p plus 1 will give you this number, and this number. So that's the logic behind it. The rest is pretty simple. You're just going to get the first element. So this is going to be the third node number. And then you're going to add plus 1 to that node number to get the third node number, just like in here, the same logic. And then the final node number here will be this plus 4 times p. Just like before, we have 4 pieces, 4 times p pieces here, so you're just adding that to the node number, the first node number. And that gives you the fourth node number. So that's it. So essentially you're adding 4p to 16, which gives you 32. And then in the second loop, you're going to add 4p to 32, which is going to give you 48, and then 64 in the final loop. So that's what's happening here. We're finding these node numbers according to this first node number. So that's what's happening here. And then else, for the elements between, I'm not going to explain this in detail because the logic is pretty much the same for the entire code. So I'm just going to copy this, and then this will be equal to let's say, just like in the uniform mesh, it's going to be 1. So in the uniform mesh, we said, if you remember, it's going to be minus 2, 1, minus 2, 2. The same logic applies here. So all I'm doing is the same thing from here. You can just go watch the video if you want to hear the logic behind it. So this is going to be 3 is equal to 2, and the index is going to be 2, just like before. And then the second one is equal to 3 plus 1, the same logic. And then this is 1, EL, 0 plus 1. All right. So this completes the elementless part. And then all we have to do here is to integrate the creation of triangular elements. So it's exactly the same. You don't have to change a single thing in this code. So you can just go ahead and copy the whole thing here and then paste it in here. And then that completes the void mesh code to generate a circular void mesh. So let's run this. I think I tried to do something here, so let's see. Oh, sorry. This has to be this. And then we have to change this to brackets. I think we made the same mistake here, so let me just correct those. So essentially, I just misplaced the brackets. That's all happening here, so we also need to correct this. All right. And then finally, I can just copy this. Oh, I think we're done. Okay. Now let's run this. I think I made another mistake here. What is that? Region number 3. Oh, okay. Yeah, the same mistake again. We forgot to change the plus signs to minus because we already covered those 2 diagonal lines, so we have to change these 2. And I probably made the same mistake here, so let's change these 2. All right. So if we run this, another mistake here. I probably made a typo here. I'm not sure what it is. I forgot to change these p+1s to p-1s. So don't forget about those in your code. They're pretty essential. It pretty much matches the sizes of these numpy arrays. So, and then finally, I think you should change this to elif block. I'm sorry, there's a lot of typos in the code, but this is the final typo, I think. So it shouldn't be a problem. So if you do this, now it should give you the correct plot. So let me show you what happens if you just do this if block. So let's say I forgot to change the typo and ran the code. Now this completely ruins the code because it changes the whole element list. So don't forget about this. Fix this in your code if you're looking and copying this code to your own files. Don't forget about this. And then if you run this, now this gives you the correct plot. And then you can also change the element type. So let's just show that. And yeah, as I've said before, the integration of D2TR3N is essentially the same as in uniform mesh code. So you can just go straight and copy this from the previous video and paste it in here. So that completes the explanation for void mesh. I hope you guys enjoyed. I'm sorry about the typos. Don't forget to change those typos in your code. And that's it. I'll see you guys in the next hands-on session. Take care.